primary and secondary alcohols can be converted to alkyl halides using a reaction with phosphorus trihalide. And so the trihalides that we can use for this reaction, as indicated up here, are PCl3, so phosphorus trichloride, or you could also use phosphorus tribromide. And either one of these will undergo an SN2 reaction with a primary or a secondary alcohol to form either an alkyl bromide or an alkyl chloride, depending on which phosphorus trihalide you use. So where this is useful is if you have a primary or secondary alcohol and you want to convert it into an alkyl halide and you don't want to use the harsh conditions of HCl or HBr. Those are both strong acids. So this is useful for a lot of things, but useful if we want to avoid the use of strong acids. So if you want, so if we don't want to use a strong acid, and so you might wonder, why wouldn't we want to use a strong acid? And if you were using a simple small alcohol like the ethanol that's shown up here, it would probably be fine to use HCl or HBr. But once we get into more complex organic molecules and things that are really useful in terms of creating pharmaceuticals and that sort of thing, you often have a lot of functional groups that are very sensitive to strong acids. And it could really destroy your molecules. So you're going to want to use more gentle conditions in those cases. So it's useful for that if you want to avoid the use of a strong acid. And it's also useful if you want more control of the stereochemistry. So if you want to control the stereochemistry. So especially with secondary alcohols, right? That's when we can have a chiral center. If we treated one of those with HX, you're going to get a carbocation intermediate. Those are SM1 reactions. And when you have a carbocation intermediate, you have absolutely no control of the stereochemistry. But with an SN2 reaction, you do have control of the stereochemistry. So I am going to draw an alcohol that happens to have a chiral center. So I'll just make a small secondary alcohol. And we'll take a look if we react this with PBr3 and pyridine. And so what pyridine is, before we get started with this, pyridine is a base and it has this structure. So it is an aromatic base, and it is a base that is not a nucleophile. So it doesn't compete in this reaction. So this is a non-nucleophilic base. So we add this simply to take an acidic proton in this solution without interfering in the reaction itself. Okay, so what happens if I take this and I add PBr3? So I am going to draw out just one of the bonds to bromine. So what I'm going to do is an initial SN2 attack of the alcohol onto that phosphorus. So the alcohol attacks the phosphorus, and we're going to kick off a bromide. So that's key. This is where we're going to get the bromide nucleophile that's going to end up in the product. Okay. And so from that first step, what we have is we have an oxygen, and it has hydrogen still attached to it, and it's got that phosphorus with two bromines on there. And so here's the hydrogen that we need to remove, and that's the role of pyridine. Pyridine is going to remove this hydrogen, but not do a nucleophilic attack. So I'm going to draw in the pyridine, and this is its role. It's just to scavenge this positive charge, so it's going to remove that acidic hydrogen. And so what we have now, our oxygen is neutral. It's got a bond to phosphorus, and that phosphorus has bonds to two bromines. And so what we've got here is a really good leaving group. So we've taken and we've transformed the alcohol into something that is a good leaving group. And so this good leaving group can now be displaced by the nucleophile that we generated in this first step. So the bromide can come in, and this is an SN2 attack, and it's going to displace that good leaving group. And so an SN2 attack, we should recall, means that your nucleophile has to approach from 180 degrees away from your leaving group. So if this leaving group is sticking out of the plane of the page, this bromide is essentially coming from behind the plane of the page and displacing that good leaving group. And so what that does to the stereochemistry, we'll see in the product, if this is coming from behind the plane of the page, now it's on a dashed bond. So it is facing away from us. So we have added the bromide and we have controlled the stereochemistry. We've inverted it, but we have complete control. Okay, so we see inversion of stereochemistry with this reaction. And you could draw this exact same mechanism with PCl3 if you wanted to add the chloride. Just in every step where you have bromine, just imagine that there is a chlorine there instead.